Hello everyone, my name is Yuke Wang. I'm the PhD candidate at the University of California at Santa Barbara. Today, I would like to introduce you our work, an efficient quantitative approach for optimizing convolutional neural networks. Let me start with some background. Convolutional neural network is popular and widely applied. It has been used in the object detection, video classification, image segmentation, and human pose estimation. Existing CNN work tries to improve accuracy or reduce complexity. Therefore, there are a lot of efficient models crafted manually, for example, like the VGG network, MobileNet, or generated from neural network architecture search. However, existing methods have two major issues. The first one is that they are missing an interpretable metric to correlate the CNN model architecture and its accuracy predictability. And the second issue is that they require huge training efforts because they need to validate their accuracy result by training hours or days. Let me give you some background of the existing convolution layers. Like the first one is the standard convolution. As we can see from this figure, each input channel will be used to generate each output channel. And later on, for all other kernels, we call it a factorized kernel. The goal of this kind of kernel is to reduce the computation capacity, at the same time reduce the number of parameters. Let's start with the pointwise convolution. For pointwise convolution, the channel mapping strategy is similar to the standard convolution. The only difference is that for pointwise convolution, instead of using 3x3 kernel, we only use 1x1 kernel for each channel. And next, we will move on to the group convolution. The group convolution will keep the same spatial dimension as the standard convolution, as we can see from the figure. And the difference of the group convolution and the standard convolution is its channel mapping. As we can see from this diagram, only two of the input channel will be mapped to each output channel. And next, I will show you an extreme case of the group convolution called the depth-wise convolution. In this extreme case, each input channel will only map to one output channel, and at the spatial dimension, the kernel size is the same as the standard convolution kernel. In the last case is the hybrid method, which combines both the group convolution and the pointwise convolution. And for all this method, they aims to reduce the parameter size while reduce the computation capacity effectively. In order to measure the effectiveness of those convolution filters, the notion of receptive field has been proposed. However, it comes with several challenges. First, receptive field quantifies the local representation ability in a single convolution layer. It could not cover the representation ability across different layers, which is very common in today's CNN network. In general, a larger receptive field leads to a higher accuracy. The second point is that receptive field usually fails to quantify the global representation ability across different kind of layers. Because modern CNN networks usually have a large number of convolution layers with diverse receptive fields stacked in a CNN stage. And in the next few slides, we will talk more details about the CNN stages. The third point is that receptive field fails to consider the channel number. However, channel information is critical in the modern convolution layers. For example, like the depth-wise convolution and the channel-wise convolution. To address those challenges, we proposed our 3D receptive field, an interpretable metric for efficient CNN architecture design. Particularly, we focus on two levels, the stage level and the kernel level. At the stage level, we decide the number of the convolution kernels in different stages, while at the kernel level, we choose the type of convolution kernel to use. For example, the standard convolution kernel or efficient factorized kernel. We build up 3DRF to unify and combine all the optimization at both levels. In this slide, I would like to introduce the key concept 3D receptive field about its details. Basically, 3D receptive field is to measure the representation ability of each neuron in a convolution layer. Here, we show some of the formulas to get the 3DRF at different layers of a CNN model. And the key insight is that the portion of the input tensor that can flow into each output neuron, which we name as 3DRF, often determines the learning potential of that given stage or kernel. A stage or kernel with large 3DRF will have more input elements passing through, leading to a higher potential for extracting useful features and improving the classification accuracy. Therefore, we use the 3DRF to estimate the quality of architecture design in search persist rather than repeated training, which generally takes days or hours. As shown in the figure below, we first decompose the CNN model into different stages, where each stages consists of a similar convolution block which share the similar structure of channels and spatial dimensions. And all these kind of structure are very common in the popular network, such as the VGG, RaceNet. For given a CNN stage, we can recursively compute the 3DRF with respect to each layer based on the stage input tensor dimension and the kernel filter size. And next, I will show you the 3DRF GANs. It is to use to quantify the representation ability change between two consecutive convolution layers. And the 3DRF GAN is sensitive to the location, type, and combination of inserted convolution layer. For instance, as shown in the figure below, for a given CNN stage, we can first compute the 3DRF for both the first and the second layer, and then apply the formula for 3DRF GAN to derive the representation change between these two layers. Next, we would like to discuss a short case study, which is the accuracy impact of 3DRF GAN. In this study, we will show you a short example of a VGG11 as the baseline structure and run it on CIFAR10 dataset. And we have 5 VGG variants by inserting a single standard convolution before each maximum pooling layer. As shown in the table 2, we can clearly figure out the impact of the 3DRF GAN on CNN model accuracy. In general, large 3DRF GAN of newly inserted layer agree with the notable accuracy gain, as is the case for variant 1 and variant 2. For variant 3, small 3DRF GAN indicates close to saturation information coverage, yielding negligible accuracy improvement from the original model. Variant 4 and variant 5 has a low 3DRF GAN of 0, indicates that inserting convolution layer does not improve its 3DRF. In fact, variant 4 and variant 5 show an accuracy degradation. This degradation shows that a 3DRF GAN of 0 signals overfitting since all input elements have already been observed by other kernel at each stage. This trend also demonstrates a strong correlation between the 3DRF GAN and the accuracy change. Thus, it guiding the AN design in terms of the insertion location for different convolution layers. In order to use such observation, we introduced our design called the stage level organizer. It basically consists of 3 steps. The first step is to find out the convolution kernel with minimum 3D-RF gain, which has the lowest contribution to 3D-RF. And second is to support the stage with a large room for improving the 3D-RF. And the third step decides whether moving the last convolution layer from the source stage to the target stage or simply removing that layer. More detail of this process can be found in our paper. Next, we would like to optimize our CNN model at the kernel level. In order to do that, we introduced our kernel level decomposer. The goal of this decomposer is to reduce the computation cost of a CNN architecture design, and we substitute the standard convolution kernels with less computationally expensive convolution blocks. And besides that, we have a rule of kernel replacement, which has two conditions. The first one is the quality condition, and the second one is the compact condition. The goal of these two conditions is to ensure the quality of our substitute kernel to achieve the equivalent predictability compared with the standard kernel, meanwhile reducing the computation and the memory overhead. The third point is, by using our kernel level decomposer, we can unify the previous construction of the convolution blocks and build a new convolution blocks and one efficient factorized kernel. To illustrate our kernel level decomposer, we also demonstrate some examples in this figure. So basically, convolution block A adopted by exception network and B applied in the mobile net follow a similar structure. Both A and B successfully maintain the same 3D-RF with the standard convolution. Specifically, the spatial coverage is managed by the depth-wise convolution, and the channel coverage is taken by the pointwise convolution, which communicates information among all input channels. Convolution block C used in the CLC net and D utilized by the shuffle net, on the other hand, achieve the same 3D-RF with the standard convolution. Next, we will discuss our evaluation. For evaluation, we use several popular CNN models, including the VGG16, VGG19, MobileNet, and RaceNet50. For VGG16 and VGG19, they are two most classical CNNs with linearly stacked layers. For MobileNet, it is the representative lightweight model with the depth-wise and pointwise convolution block. For RaceNet50, it is the representative model with the non-linearly stacked layers. In other words, the residual connections. For dataset, we use the CIFAR10, CIFAR100, and ImageNet for evaluation. In our evaluation section, we have divided into two parts. The first part, we will do the evaluation for the effectiveness of our stage level organizer. And we apply our stage level organizer on all models we discussed in the previous slides across different datasets. As we can see from the result on CIFAR10 and CIFAR100, the increase of the 3D-RF gain by properly changing the neural network stages and bring the benefits of the accuracy improvements. Meanwhile, we reduce the number of the computation and the parameter size. And we can also get the similar observation by running our stage level organizer on CNN models for ImageNet dataset, which is more challenging compared with the CIFAR10 and CIFAR100. In the second part of our evaluation, we use the kernel level optimizer based on the result of our stage level optimizer. As we can see from the table on the right-hand side, our kernel level design optimizer can generate the kernel designs that can offer large space of the performance parameter and the computation trade-offs. And this can help us to identify the potential design which has not been covered by previous kernel implementations. And thank you, that's all my talk.